Everyone has an intuitive sense of how fluids behave when poured. We typically describe the difference between water and heavy syrup as thickness. In fluid mechanics, we define this behavior as viscosity, a fluid's internal resistance to the movement of one layer over another. It is essentially fluid friction. This resistance is a quantifiable mechanical property driven by two specific microscopic mechanisms, depending entirely on whether the fluid is a liquid or a gas. In liquids, this friction is primarily caused by cohesive forces. As layers slide past each other, the molecules stick together, creating stretching, elastic-like bonds that physically resist being pulled apart. Gases behave differently. Their viscosity is driven by molecular momentum exchange. Because gas molecules move rapidly and erratically, they constantly collide and cross the boundaries between flowing layers, transferring their momentum and creating an internal drag effect. Because these physical interactions dictate how a fluid yields to stress, viscosity acts as a precise mathematical variable that engineers must calculate to predict fluid flow. This diagram illustrates a foundational rule of fluid dynamics, the no-slip condition. When a fluid moves over a solid boundary, the layer of molecules in direct contact with that surface physically locks to it. Its relative velocity is exactly zero. As we move vertically away from that solid boundary, the restrictive grip of the wall weakens. Each successive layer of fluid slips past the one below it at a slightly higher speed, generating a curved profile of velocities. If we isolate just two adjacent layers, we can measure this specific difference. We have a vertical distance between them, defined as dy, and a difference in their horizontal speeds, defined as du. This ratio, du over dy, is the velocity gradient. At the exact same time, the fluid is physically deforming. Over a specific time period, dt, the top layer travels further than the bottom layer, creating an internal angle of deformation, or shear strain, denoted by d phi. Because these layers are microscopic, the deformation angle is incredibly small. Using small angle approximation, we simplify the equation. Rearranging the terms reveals a mathematical equivalence. The rate of physical deformation over time exactly equals the velocity gradient. We have linked the visible physical stretching of the fluid directly to a rate of speed we can calculate. This geometric relationship forms the backbone of fluid friction engineering. Sir Isaac Newton established that the shear stress applied to a fluid is directly proportional to that rate of deformation. We convert this proportionality into a solvable equation by multiplying it by a specific constant. That constant, represented by the Greek letter mu, is dynamic viscosity. It is the fluid's unique coefficient of internal friction. In mechanical design, the fluid spaces we evaluate most often, like the microscopic gaps between engine parts and lubricated bearings, are incredibly thin. Because the fluid film is so thin, engineers bypass complex calculus by assuming the curved velocity profile is a straight line. The differential terms du and dy are replaced entirely by simple algebra, the total velocity v divided by the total gap thickness h. Since shear stress equals force over area, we isolate the variable we actually want to find, the shear force. The force resisting motion equals the dynamic viscosity multiplied by the velocity and the contact area divided by the fluid thickness. This streamlined linear equation gives engineers a practical algebraic tool to calculate the precise physical drag generated by a lubricant inside a moving machine. Before applying this model to a machine, we must address how viscosity is officially categorized in engineering literature. Dynamic viscosity measures a fluid's resistance to shear flow when an external force actively pushes it. Kinematic viscosity measures inherent resistance to flow under gravity alone, calculated by dividing dynamic viscosity by fluid density. You can have two entirely different fluids that require the exact same mechanical force to shear, meaning their dynamic viscosity is identical. But because they have completely different densities, the two liquids will pour at dramatically different rates under gravity. You must also watch out for unit conversions. Supplier spec sheets often list dynamic viscosity in poise, a CGS unit. To use our standard SI equations, 1 poise must be divided by 10 to yield kilograms per meter second. Mixing up external shear resistance with gravity-driven flow, or missing that 1/10 conversion factor for poise, guarantees massive errors in mechanical load predictions. Let's put this linear model to the test and calculate the exact shear force inside a high-speed rotating journal bearing. A solid 350mm shaft rotates at 300 RPM inside a fixed sleeve. The 3mm gap is filled with 6 poise oil. We translate this rotational speed into a linear tangential velocity by multiplying the angular velocity by the shaft's radius. Next, we apply our unit conversion rule to the oil. The 6 poise rating is divided by 10, yielding 0.6 standard SI units of dynamic viscosity. Now we map the circular geometry onto our linear model. If the shaft surface is unrolled, it acts just like our moving top plate, traveling at our calculated linear velocity over the 3mm fluid gap. Plugging our converted viscosity, velocity, surface area, and gap thickness into the linear formula yields the final result. The oil exerts a constant shear drag of exactly 1,450 newtons against the rotation of the shaft. By mapping the theoretical velocity gradient onto the physical dimensions of the bearing, we extracted a concrete physical drag force pulling against the machine. To keep the shaft spinning, the motor must overcome this friction. Multiplying force by the radius yields 254 Newton-meters of torque. Finally, multiplying shear force by velocity reveals a mechanical power loss of nearly 7,968 watts. That is nearly 8 kilowatts of mechanical power. Thermodynamics dictate this energy is converted directly into heat, trapped within the 3mm layer of oil. This creates a dynamic complication. As the oil absorbs thousands of watts of heat, its fundamental molecular properties change. This chart shows the effect of temperature on the viscosity of different fluids. For liquids like our oil, the line drops steeply as it heats up. If this were a gas, the viscosity would increase with temperature. Heat increases the kinetic energy of the liquid molecules. This thermal agitation weakens the cohesive bonds holding the oil together, causing its internal friction to drop. As the machine runs and the oil heats up, the drag force dynamically decreases. Newton's law of viscosity defines the dynamic link between microscopic molecular interactions and macroscopic fluid mechanics. It provides the core mathematical framework for managing the thermodynamic behavior of every real-world engineering system.